And sometimes microcontroller is undersized the problem. Okay, so in those cases also avoid microcontrollers when the problem is small and you are using a huge complex microcontroller in that system. Okay, avoid microcontrollers when you need a system where either the microcontroller is too slow to be used. Okay, sometimes you will find that there are many operations, many things, many electronic systems which need very fast processing. Okay, in such cases we should avoid microcontroller. Of course, you know how to control the speed by using two approaches. You can control the speed. One is using a high speed clock. Okay, high speed.
Sir,
Hmm,
sir, in point C, the problem is undersized for the microcontroller. That means
yeah,
it's too small to use a microcontroller, right?
yeah. Undersized means in both cases you can take it in this way. For example, you are using a microcontroller to do a very complex programming kind of stuff. Okay, or you are using a microcontroller for small issues also. So in both way, vice versa. Okay, so if you are using a microcontroller to do very complex programming, I will come to that in the last point, this one. Okay, for example, you have somewhere around 1000 images. Okay, you have 1000 images in your database and you have to select one of these images, and you have to tell which image is of the current person, of any person, or if you have to identify a person from 1000 images. In such cases, of course, microcontroller can do that task, but it will take huge amount of time. Okay, definitely it can do the task, but might be possible it will take an hour. Okay, an hour to complete the task. And by that time, if suppose you are using this kind of system for surveillance or something, then using a microcontroller is undersizing the problem in that case. Okay, so it is advisable to not to use microcontrollers. So you can of course use high speed microcontrollers. For that you can check what is the maximum clock rate the microcontroller is supporting. Second option is either you can use high speed clock, or you can optimize optimize your code. Optimizing the code means you can make it smaller, you can optimize the algorithms and so on. Okay, so there are multiple approaches by which you can optimize the code also. These two techniques you can use generally to to increase the speed of the microcontroller. But of course, you know that you cannot go beyond a particular speed when you are talking about the clock. Okay, you cannot increase the clock speed beyond the limit, because every microcontroller had its own peak clock speed which is mentioned in the data sheet. We'll come to that also. Okay, you should avoid microcontrollers when you have lots of number crunching kind of things. That means you are using lots of processing in that. Like when we say processing, you know that we have generally audio processing, we have video processing, we have image processing, and so on. Okay, and of course in the end we can say in general signal processing. Okay, so whenever you have this kind of task where you have to have the answer or the solution in a very short time period, and you have to take lots and lots of data to get to the answer or to the solution, in that case always avoid microcontrollers, because microcontrollers, like I said, are not that fast. Of course they are increasing now, they are having quite good speed, but in general microcontrollers are slower than microprocessors. Okay, so remember, in such case you should opt microprocessors, and you should go for if you are needing a processing kind of system, then stick with microprocessors, where you can do lots of mathematical tasks in the background and then come to a conclusion. Okay, so in such cases avoid microcontrollers. Now, in any embedded system, we generally have some blocks with us. Okay, and those blocks can be arranged in a particular way, and we can get an outcome. If you talk about a complete system, embedded system, then of course we will have some important parts of the micro embedded system. Am I audible? Hello.
Yes, sir.
Okay. So some of the important parts. Let me start with this particular thing: power source, or we can say power supply, which most of the people think is not that important in any embedded system, but power source or power supply plays a very, very vital role to design a quality embedded system. Okay, if the power source itself has noise, assume, okay, if we have a power supply which has its own noise, in that case we will be having a noisy embedded system which will be switching randomly on and off Okay, so you should avoid noisy power source. We will come to that, what noise actually here stands for. Okay, when we use this kind of words in embedded system or electronics, students generally go and say, okay, noise, which noise? It is not shouting or a uh, noise from the sound or noise from the light. Which kind of noise is actually affecting the whole system? So there are many different types of noises. We'll come to that, or why it is important to have a very good power source. So user interface, of course you will have some switches. Okay, switches or keyboards, and with that the user will be interfacing or dealing with the whole embedded system. Then that goes to a controller hardware. When we say controller hardware, it is microcontroller that we are using. Okay, and when we say software, we are talking about the software or the codes which we are using. Okay, so controller hardware will comprise of two things. Controller hardware will comprise of your microcontrollers, and software will be controlled by the codes or all. And then of course you will have the power interface. Power interface means, because remember microcontrollers are generally low power devices. Okay, so that means you cannot drive a motor or a tube light or a fan or any high power electrical equipment using microcontroller. So definitely to increase the amplitude of the signal or to the power of the signal coming from the microcontroller, we always have to depend on some power interface that will increase the power of the system. Then of course you will have actuators at the output. Actuators, like I said, motors, fans and all. Okay, motors, fan, or any device which can convert electrical energy to motion. Okay, mostly. So those kind of devices will be there at the output. And then of course you will have to have a control system. Control system of course is one of the most important subjects in engineering. Okay, control system will generally talk about feedbacks and all. Feedbacks, okay, and all. Feedback means positive feedback. Do you need positive feedback? Do you need negative feedback? How to control the system to get a constant output? Then that can be used again to control some actuators. Signal conditioners. Uh, which kind of signal conditioners have you studied till date? Signal conditioner. What does that mean? Anyone? Which kind of signal conditioners have you studied in your engineering till date? Or why it is necessary?
Comparative.
Hmm?
So comparators,
Okay, comparators and
filters,
what?
filters.
Filter. Yes, filters. Okay, comparators. Why we need comparators? Because look, when you are connecting any mechanical device or any analog device to microcontroller, then definitely these are digital in nature. Okay, digital means they will be working on either zeros or ones. Okay, either they will be taking input as a 0 or 1, low voltage, high voltage, or they will be providing at the output low voltage and high voltage. But these 0 and 1 are not always ideal in nature. Okay, so they may look like something like this. Like this. So in this case, this particular part is our low voltage part, and this is your high voltage part. Okay. So definitely every embedded system will have a threshold above which you will call the voltage to be high, or you will call it 1, or below that voltage you will call it 0. So comparators are very important because most of the why these particular spikes are there. Of course, one of the major reason is your power supply. Power supplies do not provide always a constant DC voltage. They will have some harmonics in them, harmonics or noise in them. So those are contributing here. At the same time, noise coming from the external world, electromagnetic signals or any other electromagnetic signal like motors or transformers which are nearby your embedded system, they will also generate this kind of noise in the system. So therefore, we need to have clean signal rather than this. For that, what we need, suppose we take an example of comparator. In that case, comparator, what it will do, it will give you pure signal like this. It will either take you 0 or 1. Okay. So in such cases, you will have to have signal conditioners so that sometimes even if there is some spike like this, though the spike is there, it is not high enough to switch on. But sometimes the microcontroller may get switched by this kind of signals. So therefore, comparators are necessary. Now coming to filters. Okay, let me draw again a square wave. Okay. This is your square wave where you consider it 0 and 1. Okay. So when this square wave is distorted, like I showed before, it will be something like this. Okay. So now there are multiple frequencies along with the square wave. Okay. First question, how many frequencies are needed to develop a square wave? How many frequencies are required to generate a square wave? Okay, let me rephrase my question. If I have a sine wave like this, okay, so in this, of course, assume this is a pure sine wave. In that case, how many frequencies are there in this sine wave?
सर यूनिफॉर्म है तो सर वन ही एक ही फ्रीक्वेंसी होगी सर
Okay,
यूनिफॉर्म साइन
so if there is a sine wave, pure sine wave, okay, pure sine wave, then we will have only one frequency like this. Can you correlate where you have studied this kind of things? That means here in this, you have in the y-axis, you have amplitude, in the x-axis, you have time, whereas
Fourier series.
yes, so you need Fourier, okay, to transform or to extract how many different signals are there in a sine wave, or different frequencies are there in a signal. So if it is a pure sine wave, you will get a pure one single spike, amplitude versus frequency. Okay. But for that, this was a sine wave. Now, how many such frequencies or signals are needed to generate a square wave? How many different frequencies or signals are required to generate a square wave? If I say pure square wave. Any idea?
Infinite.
Infinite. So if you have many sine waves, like this is a low frequency. So if you have, now if you combine these two, there will be two spikes. Okay. One is frequency F1, and there you have frequency F2. And here you have F1 and F2. Higher frequency at the higher frequency end. Okay. So F2. So if you combine more and more and more of these kind of sine waves, you will end up in a square wave. Remember these things. Okay. So when you have this kind of signals, where again in the square wave you have some distortions, so the best way to filter out or to remove these kind of spikes is by using filters. Okay. Why? Because filters, like you might be knowing, there are low pass filters, high pass filters, okay, and band pass filters and band stop filters. So now you can use filters to remove unwanted frequencies. From, for example, if this particular frequency is not needed, you can use a band pass filter with this kind of behavior, okay, and it will remove all other frequencies from the band, and you will get only the frequency of your interest. Okay, so that is band pass filter. Or you can use another approach like this. You have frequency f1, you have frequency f2, and you don't want f2, assume. Okay, so this is your amplitude and this is your frequency axis. Okay, so if you don't need f2, so you can also use a band low pass filter like this if f2 is far away from the f1. Okay, so you can use a band low pass filter also, that will also remove f2 from the signal, and you will get the original frequency f1. Filters, comparators, and any other device which can help us in designing signal conditioners. Most of the op-amp related designs are signal conditioners. You might be recalling there is one particular device called just like comparator. Any other device which is near to the comparator's behavior? Any other device? Have you heard of this word? Anyone? Smith trigger. Have you heard of Smith trigger? Please go and revisit all these things. Why it is needed? Why you studied these things? Okay. Smith triggers are just like comparators, but in the comparator you always have zeros and one, but you can switch the lower voltage and higher voltage thresholds using Smith trigger. In here, comparator you can only have one voltage level which is deciding here, okay, which is deciding the threshold. In Smith trigger you can have two levels like this, lower threshold level and higher threshold level. That means above that it will be 1, and below that lower value or lower threshold you will have 0. So this is more, you can say, precise or more accurate design compared to a comparator. Okay, so keep these things in mind, that Smith trigger provides you two threshold values. Okay, two threshold values. Okay, whereas comparator only provides you one threshold value. One threshold value is very risky most of the time, because sometimes a small spike like this even can trigger to the higher value, but in this case no, it will not switch, or it will only switch when you actually crosses the higher threshold value also. So remember this thing. So signal conditioner is very important, and of course then there will be a feedback which again goes to the microcontroller to further provide more robust interfacing with the signals. Okay, and of course you will need a power source to to provide power to signal conditioners, user interfaces, microcontrollers, and all actuators and all. Okay, so these are very important design. Okay, so when we are designing a system, we will have to have all these things in mind when we actually play around any embedded system. And remember again, these, when I am showing all these blocks, you can master any of these blocks and you can make a career out of it. It is not necessary that you always have to focus on this part only, that is microcontroller and programming. You can of course go and develop beautiful neat power supplies. You can develop very good actuators, precise actuators which can rotate at a very precise angle. For example, you might be using motors. Okay, in the motors, mostly when you are using DC motor, when you give the power, it starts rotating, and the moment you stop the power, it still keeps on running. It is not necessary that you always use DC power, DC motor, because in such cases, even after disconnecting the power, the motor keeps on running. But suppose I need a system where the moment I want to stop the power and the motor should stop. Which kind of motor should I use? My question is DC motor. If you take an example, fan is a good example of DC kind of stuff. Motor behavior is almost same. Okay, so in that case, even if you switch off the fan keeps on rotating and comes to still after some time. But assume I don't need this kind of system. I need a motor where the moment I switch off the power, the motor should stop, break. What kind of motor should I use there? कि जहां पावर निकालते ही the motor should stop. What kind of system or what kind of motor can you use in such systems? So this is again a question for you. Okay, so there are many motors. There are stepper motors. Okay, you might have heard stepper motors. There are servo motors, and these motors, all these motors have their own behaviors, all specifications. Okay, how many of you have used vending machine? Vending machine. I believe almost all of you have used vending machine where you put some money in that and it gives you a chocolate or a Coke can or something like that. Assume if you put the money and if you are using a DC motor, the motor will keep on running, and even after some time might be possible you put one coin to get one chocolate. If you are using a DC motor, it will give you 3, 4 or 5 chocolates in that case, which is not needed by any supplier. So in that case, you should not use DC motor. So of course, embedded system designer goes through all these blocks and he can master any of these blocks and can survive in the embedded system design business, because there are so many things to learn in all these blocks. Okay. Now, so
Sir, why do we need two separate power sources?
because
Why can't we use a single
okay,
source?
this one is just to increase the power of the microcontroller's output. Remember, this is just increasing the power of the, for example, you are using switch or you are using high power supply to drive the actuator. But here, this power supply is, you, for example, for the keypad. For the keypad, you might be using a 5-volt power supply or 12-volt supply. Okay, 12-volt supply is enough to drive some ICs, right? But here, you might be using 220-volt or might be using 150-volt. Depends, because you want to drive an actuator. It is two different powers. So again, there are multiple types of power sources in one embedded system. Okay, so those power systems are always needed to drive many things. Okay, let me just give you an example where you can see multiple power supplies. Any other doubt? Okay, just
Sir, if we just have to convert the low power of this microcontroller into high power, why can't we use like a power amplifier instead of a power
power
source?
amplifier. Look, first thing, when you say this kind of words, okay, like power amplifier, something like that, not Android. Wait. How do you know? So when you use this kind of words, in that time, you must know what you are talking about. Power amplifiers are different. That is to amplify the power. Power amplifiers are not used to drive fan or something. Okay, of course, power amplifiers are used in many other applications, like you are using a DJ system or something. In that case, of course, you are using power amplifiers, but power amplifiers are not the only thing which actually gives the power. Power means sometimes you might be might need relays where you need direct power at the output. Okay, so let me just, oh, this image is not good. Let me just take one of the best images. Okay, like this. No, Okay, like this. Power amplifier is a different thing. Look, when you are saying power amplifier, I will come to that later. Okay. In this in this image, okay, in this image, there are many sources of power in the Arduino. Okay. For example, this one. This one is a source by which you can drive DC power directly into the system. For this, you can use 12 volt. Here you have in this part, this particular IC is your regulator, 3.3 volt regulator. So it is providing voltage to some other circuitries also, 3.3 volt. Okay. Then you have again USB, which can provide you 5 volt precise. And here from here, you can also provide V in, you can provide 12 volts also, which actually goes to this 3.3 or 5 volt regulator is again there, which actually drives this whole system. So it is not necessary that you will have only one power source to drive the system. When we are saying system means you may have so many things. Power amplifiers, when you are saying power amplifiers, you have not gone through the course where you have studied power amplifiers. Might be that's the reason you are quoting power amplifiers can be used here. Power amplifiers, have you heard of power amplifier A, B, C, D, E, all this kind of power amplifiers? Have you heard of power
No, sir,
amplifier?
not yet.
Class A, class B, class C, class D power amplifiers. So these are different things. These are different amplifiers which actually improves the power. Okay, they will have their own efficiency, they will have their own challenges to design. But for example, you are having a microcontroller, okay, assume at Mega 328, okay, and you want to drive a 220 volt bulb. Okay, in that case, this power interface device or the power interfacing device will be not providing it will take this 5 volt from the output of your Atmega 328 and it has to drive 220 volt. For that, it will use either a relay, okay, relay, which is a mechanical switch, or it may use MOSFETs, okay, MOSFET to switch any other circuit which can switch the power supply LED or the bulb, 220 volt bulb. So this supply or this interface is different from this interface where you can use a small battery. It can act as a power source, a battery which can provide 5 volts and 1 ampere. So this power is different from this power. Okay. So there are many different things you can study. So power, when you are saying, these are for low power applications. Okay. So to drive ICs, keyboards, LCD panels or so on. Okay. Now system needing control. Almost every system in this world needs some control. And for that control, we need coding and algorithms. Okay. Systems like mechanical systems, car or any automobile or conveyor belts, they need control, the speed of that. Then electrical systems like fan, LED bulbs, television, washing machine, so on. Electromechanical, washing machine is a good example of electromechanical devices. Even electrical vehicles are good example. Biological systems, like when you are designing your vaccines or any other medicines, in that case you need control, because you cannot go and rotate the test tube beyond a certain speed, otherwise the test tube might break or so on. Similarly, when you are developing tablets or so, thermodynamics, when heat transfer is taking place, chemical testing and so on. So these are all examples where you have control, and whenever there is a control needed, you can always switch to embedded systems. Okay, embedded systems will provide that control. And so therefore, again, like I said, there are so many fields in which you can switch to a career using embedded system. And that means embedded system designer should be able to understand the basics of almost all the things when he is trying to get into that domain. For example, if you want to develop devices for medical instrumentation, so you must be able to understand what are the biological needs of the instrument. You cannot go and fix a layman's kind of motor or something. You cannot take a hexa blade and start cutting a human being. You have to have a very precise medical instrumentation, at the same time control over that device. One of the examples of such a control system you can see here, I believe you might be knowing this particular system, but still this is one of the good examples of a precise control system. Let me just show you. Okay, this particular. You might have seen this kind of jigsaws or saws which are used to cut the woods. Okay, but sometimes this can even cut your finger. Okay, or your hand also. But now this device can be controlled using embedded system, and it will stop the moment a finger is coming in with this in touch with this particular device. So the blades of this particular system, wait a second, blades of this system are having sensors, and they can stop the moment it comes in touch with any kind of flesh. And this is a braking system. So there are so many other examples, but assume the precision of this particular system. You see, it will not cut your finger, and it will automatically break the system. Remember, the blades are rotating at a speed of somewhere 10,000 RPM to 20,000 RPM. Even at that speed, you can stop a blade and avoid accidents using this particular technology. So there are so many things you can develop. Okay, so this is one of the examples of such technologies where you can have control, because control means even breaking a system is a control. Okay, so now major components. What are the components which actually makes an embedded system? Of course, we saw the block diagram, which comprises of many things which makes an embedded system. If we go a bit deeper into that, we can come across many other such systems, like amplifiers are there, signal to amplify the signals. There are filters, custom logics. Custom logics means you have your own logics. So this is there. You can have counters, timers, UART for communication. Timers are there. PWM systems, which pulse width modulation systems, digital to analog converters, special systems to drive LCD, analog to digital converters. That means you can have so many different blocks of electronic systems which are embedded into one system. Okay, so these are all embedded, and that makes the embedded system. So you are embedding many different small blocks of electronic systems into one particular chip, and that will make an embedded system. For example, if tomorrow you want to have wireless connectivity to my microcontroller, you can embed that also into a system. Similarly, if you want to have connectivity using USB, you can embed into that. So this kind of features, that means include more and more electronic systems into one particular system, is called embedded system. Okay, so that means you can have almost everything embedded into a chip, and that will make your system embedded system. Okay, similarly, there are another approaches, like you can have op-amps or separate systems for controlling the LEDs or LCDs or PWM systems and so on. Okay, and of course, in the core, in the most important part of any embedded system is the microcontroller itself. Okay, which will do the processing part. So it will be taking inputs from either the ADCs, DACs, or any other system, and it will process it and give some output for the customer or for the user, and therefore you have to have a microcontroller into that. So these are the basic building blocks in any embedded system. And remember, like I said, you can master or you can develop mastery in even one of these technologies and survive in embedded technologies world. But of course, you have to have very solid knowledge about these things. You have to have very good deep knowledge to modify these things for particular applications. Okay. And of course, you can survive in embedded systems domain. So there are so many things that you can do. It is not just coding C, C++ code kind of stuff. Okay. Let me take an example. When I said power sources, power supplies, okay, why they are important and why a normal engineer or normal student do not know the basics of embedded system, why they are deprived of actual knowledge or the core essence of embedded system. Mostly the people or the student think that, okay, you just have to write a code and you will become an embedded system designer. No, it is not only coding. It is a combination of electronics engineering, like analog engineering, digital engineering, at the same time coding also. Okay, so these three will make a good embedded engineer. For example, when we say power supply, you might have used power supplies in the lab also, where you get this 5 volt, 12 volt, 24 volt kind of stuffs. These are voltages. Okay, these are only voltages. These are not specifying the current here. Power, when we say power, it actually combines both. Okay, P is equal to VI, that means combination of voltage and current. So you can have, or you can design systems like 5 volt 1 ampere, okay, or 5 volt 2 ampere, or so on. You can make the permutation combination. You can have so many different requirements by different users. So let us just briefly look into the important part, why generally engineers or people think that, okay, embedded system only means coding, and they actually fail when we go to depth. Okay, so now here, how many of you actually know this is one of the power supplies, okay, designed by Keysight. Keysight is one of the major electronics or electronics manufacturers. Okay, they design quality products, and of course there are many other such companies, but still let us just briefly look into the specifications. It is not only about 5 volt or 12 volt. Okay, how many of you can actually talk about these particular things like power output? How many of you have talked about power output of the supply in our lab? What is the power output of our lab's power supply? This particular part, power output. You have used power supply in the lab, but do you know what is the actual wattage or output wattage of those power supplies? What is that? What in terms of what? The power in terms of what? Okay, can you justify that this particular model 36311 is 80 watt by looking into this data sheet? Anything you can look into that, and can you come up to this value 80 watt? Anyone? Why they are calling this power supply 80 watt power supply and this one is 160 watt power supply? Why? By looking into this data sheet, can anyone come to that number? Anyone?
सर पहले वाले में
सर तो
6 into 5 करेंगे तो 30 हो जाएगा और 25 into 1 करेंगे प्लस 25 into 1 करेंगे तो सर
Yeah. So this is the actual calculation here. Why they are calling it 80 watt? Because 25 into 1, okay, that is 25 watt. 25 into 1, 25 watt, 25 plus 25, 50 watt. Okay. 6 volt, 5 ampere. Now see the difference here. You have 25 volt, but low current, 6 volt, but high current. And this is making you or providing you 30 watt here. Okay. 50 plus 30 is 80 watt. And similarly, you can do the calculation here also. So it is not just small 80 watt power supply, but you have to understand where it is actually delivering you that power. Okay. So when you are going to purchase a power supply, remember this kind of stuff. You have to go and understand these things. Okay. How many of you remember this particular term? Load regulation. And see what does that mean here? Here, what it means here. Load regulation. Anyone who remembers what is load regulation? Load means the thing that you are using to drive or we are connecting with the power supply, like resistors, motors, LEDs, or any other device. So now load regulation means with respect to change in load, how much percentage of the actual voltage is going to change from the power supply's side. For example, here we are focusing on 6 volt. This is our main voltage, one of the voltage which we are going to use, 6 volt. Okay. If suppose I connect this any particular load like 1 kilo ohm, 10 kilo ohm, 100 ohm to this 6 volt, how much this 6 volt is going to deviate from itself. People might think that why we have to worry about that. Okay, let me give you an example. Okay, so I have a supply. I have a power supply PS, and it is providing me, like in our example, 6 volt. Okay, and we have ground here. Okay, you used a multimeter to measure the voltage. So you connected one of the terminal here and one of the terminal here, and you observed that it is 6 volt. Perfect, no issues. This is 6 volt because right now it is open circuit. There is no load connected to this particular power supply. But the moment, assume I am going to the extreme. Okay, I am going to the extreme now. Assume I came up with a short circuit. I took a wire and connected these two, and assume this wire is thick enough to sustain the power. So now when I connect with a short circuit, what will be the voltage if I use the multimeter here again? The same multimeter, if I connect here, what will be the voltage here? In that case, will it be 6 volt?
No, sir.
Then what will be the voltage here? Okay. Of course, you know that when we short circuit two terminals, the voltage difference between the two becomes 0. So that's why you will get 0 volt. Now the question is, the power supply maker told that it will constantly give 6 volt to different loads. But no, it is not correct. It is not guaranteeing 6 volt for each and every load that you are connecting. Okay, load that you are connecting. So how that specification comes from the power supplies manufacturer side? It talks about load regulation, how the voltage is going to change with respect to the load. Okay, so now very good company will provide very small values, like here you see 0.01% plus 2 millivolt. So the load, if you keep on changing the load, there might be a load. That means this voltage 6 volt may change 0.01%. Okay, with respect to the load that you are connecting. Similarly, the current that you are expecting, like 5 ampere, may also change by 0.01% plus 250 microampere. Whereas if you go and now take a power supply specification from any other user or any other manufacturer, you will find that there is suppose 10% change. So that power supply is not that good compared to this power supply. Okay, line regulation. What does that mean? Why these things are important? First thing, why these things are important while designing an embedded system, or why should the embedded system designer should know all these terminologies? First, what is line regulation? Then why it is necessary for an embedded system designer to know? What is line regulation? First question. Like the load was at the output. Okay, we had the power supply, okay, PS, and at the output section we had 6 volt, okay, and ground. So that means any change in 6 volt due to the load, change in load will be termed as load regulation. That means change in 6 volt due to load is called load regulation. But what happens if we change the supply voltage? We are expecting 220 volt at the supply for this particular voltage power supply. Okay, so this is 220 volt, 5 ampere provided by our electricity board. But what will happen to this 6 volt if this voltage is dropped to 110 volt? Will the 6 volt remain 6 volt, or it will also decrease with respect to the voltage change? Or assume there is a sudden spike due to lightning or something, and this voltage suddenly jumped to 260 volt for a small time period. In that time period, what will be the voltage here for that small time period? And this is called line regulation. Okay, line regulation. That means change in this 6 volt with the change in the line or the supply, power supply, main supply, is called line regulation. Load regulation is a change in this particular 6 volt with change in the load is called load regulation. So there are two, now these are two specifications are there which are for power supply. Now coming to the another features. Output ripple. What does that mean? And why it is necessary for any embedded system designer? Output ripple. Output ripple from the power supply. Because remember again, every power supply that you design, okay, whenever we design a power supply, if we are designing a DC power supply, we are saying, okay, 6 volt and ground, okay. So ground, if I measure ground, it should be always 0 volt, okay, like this, and 6 volt, that means 6 volt like this, 6 volt, okay. This is amplitude in volt, and this is time. This is 6 volt. Now, if you amplify this particular zone, or if you zoom into that zone, will this particular line be steady, or if you zoom in, will this line be something like this or something like this? Like this. Actually, it is not possible to design a pure DC voltage supply, because every supply will have its own ripple. Okay, there will be some small ripples in nano volt or micro volt. There will be some ripples in the supply, and it also changes with respect to the load that you are connecting. Okay, of course, the behavior of the load, like it is resistive in nature, capacitive in nature, inductive in nature, or even when the load is changing like 2 ohm, 10 ohm, 200 ohm, 2K, 20K or so on. These ripple actually changes its amplitude with respect to the load that you are connecting. Okay, so this is called ripple output, and it also changes. So now, what is the specification provided by the power supply manufacturer? It also plays a very important role. So for different frequencies, it's saying that we have this much of normal output ripple with respect to this much voltage change in the output. So 2 millivolt That means 350 microvolt RMS per 2 volt peak to peak change. Okay, 2 millivolt peak to peak change. So these kind of things are important. Again, have you came across this kind of stuff? Accuracy 12 month. That means all the specifications that they have provided for 12 months it will remain same, but at 20 degrees Celsius plus minus 5 degrees Celsius. So that means you can expect the same results which are provided in the data sheet for 12 months when the temperature is 23 degrees Celsius plus minus 5 degrees. That means 28 degrees Celsius, or it may be 18 degrees Celsius. For that range of 18 degree to 28 degrees Celsius, you will get all the results. So these kind of stuffs must be kept in mind before designing a system. Even if you are designing your own power supply for the embedded system, then again there are so many other parameters. How many of these parameters actually you know? And the more you know about these parameters, the more you will be becoming a good or a better embedded system designer. So there are so many things that you can go and check. Okay. Okay. Like how many of you know this part? Overload protection, over voltage, over current. Have you heard of over voltage protection? Over voltage. That means when there is a lightning or something, suddenly the power supply gets a huge voltage. And this power supply can sustain that voltage for 5 milliseconds. It cannot sustain more than that. That means even if there is a lightning and that spike is just for 5 milliseconds, within 5 milliseconds, then this power supply can handle that kind of over voltages. But if that voltage is continuously higher than the expected voltage, that means if it is greater than 5 milliseconds time period, then the voltage supply will not guarantee you constant 6 volt. Okay, this kind of stuffs are very important when you are dealing with the power supply. Similarly, each and every product that you see in any embedded system, do go and study their data sheet and check the technical terms which are provided there. It is not just 5 volt or 12 volt, 1 ampere, 24 volt, 1 ampere. There are so many things other than just voltage and currents. Okay. Okay, power interfaces. Okay, leave it. There are power supplies which uses PWM mode to generate or change the voltages at the output. Okay. Okay, let me just go for an example. Assume you have a power supply. Okay, you have a power supply here. Power supply. And that power supply is supplying voltage to your microcontroller, MCU. Okay, here you have the ground and here you have 5 volt. Okay, and this microcontroller is providing output 5 volt to trigger some relay. Okay, or you are using, might be possible you are using a transistor. Okay, transistor to drive a motor. This is a motor, and you know that motor cannot be driven by microcontroller unit. Microcontroller will provide 5 volt, but generally the current here is of very low power or low ampere. Okay, so I like 20 milliampere. If anyone recall what is the output current provided by Atmega 328 or Arduino Uno? Arduino Uno. What is the output current provided by Arduino Uno? 5 volt, and how much current? Anyone? Because you should know this.
Around 40 milliampere.
40 milliampere. From Arduino Uno, you get 40 milliampere. Okay, remember this thing. So that is ideal number. Okay, so 40 milliampere current you can use to drive any load. So you can use LEDs and so, but it cannot drive a motor because motor needs, assume 5 volt and it needs 500 milliampere. Now the game has changed. Microcontroller can provide you only 20 milliampere, but here it needs 500 milliampere, though the voltage is same. So what you can do here is assume your power supply can provide 5 volt and 2 ampere. Okay, so it has got enough power to drive the microcontroller unit because it needs only small current at the output. But so you can use this same power supply to drive the motor. Okay, so now how many of you think that this particular system is good? Or whenever there will be one output, one, okay, high, okay, we can call high, the motor will run. How many of you think that the motor will run whenever the microcontroller is providing you high? Circuit is correct. Okay, circuit is correct. Because look, at the base, when the base is high, the transistor will act as a short circuit. That means it will act as a short circuit. And all the power that is here, 5 volt and 2 ampere is here. So don't have to worry about the current also. So it needs only 500 milliampere. So it is enough current. So the transistor is acting as a short circuit. So the motor is getting enough power to run. So now how many of you think this system will work? Or if you think this system will not work, then what will be the reason behind it?
So shouldn't we provide more collector voltage in order to amplify the input current to
No,
drive the motor?
because microcontroller is at 5 volt 20 milliampere. No, it cannot go beyond 20 milliampere. So don't have to worry about that. Any other answer? Any other answer? Why the motor? First, how many of you think that this system will work? System will work. First of all, how many of you think that this system will work? Raise your hand. You have the facility to raise hand in this, I think. So, how many of you think it will work? And how many of you think it will not work? Wait a second. Okay, I have to keep it here. Sorry. How many of you think it will work? First of all, I believe it will not work. Or even if it works, it will not consistently work in a correct way. The reason, anyone, why I am thinking that it will not work properly for a long time period?
So current is more 500 milliampere is required only for the motor.
So what? So
And
power supply can provide, na? 2 ampere is going towards 2 ampere, 500 milliampere. If it takes, still it has got enough power. At 2 ampere, the motor will take 500 milliampere, 20 milliampere by the MCU. Assume, okay. So 520 milliampere, 5 volt. It can deliver you power 5 volt into 2. That means 10 watt. Power supply is of 10 watt. But the system is only requiring only 5 volt into 520 milliampere. So the system is requiring less power. Na? So the power is not an issue here. Power is not an issue here. Then what is the issue? Okay, I will give you a hint. We need a signal conditioner in this system. Why and where? We need a signal conditioner. Okay, how many of you know that motor, when we say motor, I am representing the motor by a winding or something like this. What is representing here?
inductor.
Inductor. So now when you are using an inductor, okay, in the system, what can happen? Inductor can generate oscillations in a system. Okay, the motor, when the motor starts, you will find that this DC voltage 5 volt power supply actually starts changing its behavior. it generates spike in the system. So the power supply that we see here will generate spike here also at this microcontroller side also. So the microcontroller might possibly switch on and off, on and off, on and off again and again. Understood? So because of the motor, the power supply may get spikes, and those spikes can even distort the input at the microcontroller. Microcontroller will run only if it is having 5 volt. The moment there is a spike, a negative spike somewhere around 2 volt or so, if the microcontroller goes beyond less than 2 volt or so, the microcontroller will stop. But the moment the microcontroller stop, this particular becomes low, the switch will become off, again the motor will stop, the power supply will not have any spike. So this is a kind of, you can see that this is becoming a loop, feedback kind of stuff, which will keep on switching the microcontroller on off, on off, on off, on off, and the motor will run for very small time period, but you will not be able to see that. Why? Because the motor will keep on running. It will not stop, because this spike may be of some nanoseconds, milliseconds. So the microcontroller is switching on and off for milliseconds, and the motor will keep on running. You might be thinking that the whole system is running without any error, but in actual, the power supply is switching on and off again and again. Try it, you will be able to see that effect. Okay, now, so sometimes even when the system is running smoothly, you might be able to find that it is having some errors in it. It's not just the system is running. Okay, you might have some errors in that also. Okay, controller hardware, we generally have analog and digital ICs. Okay, we will have microcontrollers in them. We will have some communication circuits for communication with the external world, and definitely there will be some circuitry involved, like the circuitry we developed right now in the example. So there will be pull up, pull down resistors and analog processing ICs and so on. Okay, so it is not just microcontroller and a motor. You will have to go through to the basics to and fro again and again to master the embedded systems. So keep on studying these things. Okay, now when we say the software part, in the software part we will have some languages. Preferably I am going to use C or C++, embedded C. Okay, or you can have some IDEs like Arduino IDE, IAR, Kyle, or something like that. Okay, you can also use languages like assembly languages for high speed functionalities. We will come to the comparison between assembly and any other language, high level language. So of course, for high speed purposes, you should go and use assembly languages, or you can also go and use VSDL to generate very high speed systems using FPGAs. Okay, so software is one of the major component to increase the speed. Like I told in the beginning, there are two components. One is either change the speed of the clock or change the type or the way you are coding something. Make optimal coding. Okay, optimized coding. Now, let us briefly understand why this subject is important again. Okay, and try to understand some of the important things that will actually motivate you to get into this subject. Okay, so first I have taken this from one of the surveys. Yesterday I did some research to find how can we actually look into the emphasis of embedded system, how these are going to help the students. Okay, why you should go and study these subjects. Okay, there was a survey conducted by one of the company called EE Times. Okay, EE Times is a website. I will share you the document later. And they questioned the embedded system designers, so many different questions to those embedded system designers, and they come up with a conclusion. So in general, nowadays, around approximately 30% engineers are working in industrial control or automation. So if you are focusing in that direction, you will be having a good chance to get absorbed into a company. So industrial automation and control. Okay, so if you are interested in that domain, if you are working or developing some project in those domains, you can get good jobs. Consumer electronics, again almost 30%. Now you can see in 2017 it was only 21% consumer electronics, but by 2019 it has raised to 29%. So there is a 7% increase in consumer electronics. So you can talk about all different kind of embedded systems that are there. Again, there is a huge demand in IoT also. From 19% in 2015, okay, 2015 it was only 19%, and 19% engineers were working in IoT. Now almost 25% engineers are working in IoT related jobs. So there again you can go and design something related to IoTs to get into that. And you can see there was a huge demand in wireless communication kind of stuff, networking related stuff in embedded, but it is slowly decreasing, but we cannot predict that because it is only 2% small change. Okay, automotive is almost stable, but my personal view is that in the coming years automotive engine world will definitely be using more and more embedded systems because of driverless cars and of course self-driving car. Not only that, there are so many other features which are going to be embedded into a car. Medical industry, of course there is a huge boom in medical industry due to corona and all. Okay, robots and lots of robotics or self what to say, patient care systems are developed in embedded. So there is huge demand. So if you are focused in embedded, then you should go and try in these sectors. Military and aerospace, of course there is a small people, there are very few people who are working in military, but of course the market price is very high. Defense gives you the highest amount of money. Okay, so very rare engineers will be working in defense. Okay, this is one of the things that you can keep in mind. Of course, there are people who are working in video and image processing, audio processing, government or municipal, and all those stuffs. Okay. Now, how much time an engineer is spending in embedded system in which particular task? So, if there is a project to be completed, so most of the time, what the engineers are doing, then you can focus here. Most of the time, engineers are designing about or discussing about the design details. What kind of design you have to develop, what kind of details you have to include in the system. So 30% of the time is actually spent in discussing these things, designs, details. Okay. Now, after that, you can see most of the time engineers are spending in testing and debugging. So once they have the design details in their hand, they start developing the design and test and debug the program or debug the hardware or debug the software. So 19 to 20% of the time they are busy in debugging and testing. So in total, you can see almost 50% of any project's time period is spent to discuss the designs detail, and 50 that means and test and debug the system. Rest of the system, that means developing the specifications of a system, what particular frequency is needed, what temperature is needed, what particular rotation of the motor is needed. These kind of things takes almost 10% of the time. And prototyping, that means basic first model to run, it takes almost 10% of the time. So remember, 50% of the time is discussion and testing and debugging. Okay, so this is very important. So you have, if you want to survive in this domain, then remember most of your time will be spent discussing the designs, behavior, and testing and debugging. So you should be handy with the instruments that you use, like soldering iron, multimeter, oscilloscopes, spectrum analyzer, and so on. Okay. Now, there are two things again we can discuss, like most of these technologies, what kind of outputs are they coming up? That means what kind of products are they developing using embedded system? So now you can see there is a huge demand in machine learning related projects. Okay, so huge demand is there in machine learning. So people in 2019, most of the people are considering to work in machine learning. This was conducted in November or December 2019. So it is very 1 year, 1 year back. Okay, so it is almost latest report. So most of the engineers are trying to move towards embedded systems using machine learning. Okay, and embedded vision, video processing and all. Okay, it is 43% of the people are actually currently either they are using or they are planning to move in that domain. Okay, so AI and cognitive, more you get from the trend you can see, 55 plus 38. Okay, so almost 40 plus 55. Okay, so almost 90% engineers, okay, are interested towards AI and machine learning, and they are interested to work in that domain only. On virtual reality, like VR enabled headsets and all, they are there, but 90% of the engineers are considering to move into this domain. So these two domains are very hot. So even if you enter into these domains, you can survive for at least 5 to 10 years, maybe. Okay. Okay. What kind of languages are these engineers using? In embedded system, still most of the engineers are using C. You can see 2017 to 2019, 56% engineers are still working with embedded C. Then rest of the engineers are working with almost C++. So 25% are working with C++. So if you take this 60 plus 25, almost 85% engineers are working with either C or C++. Okay, majority working with C. Then of course there is a huge increase in the volume of the engineers who are inclining or moving towards Python. So it has doubled, almost doubled. 2017 there were only 3% engineers who were using Python in embedded systems. Now almost 6% engineers are using Python. So it is a good scope to work in Python also, but still the king is C. Okay, they are using Java, MATLAB, LabVIEW, JavaScript is there, C# is there. So these are the major languages which are used in the industry, embedded systems industry. But still you can see here 4% engineers are working with assembly languages, which is the most or the oldest language you can say. Okay, so it is the most basic language, but still 4% engineers are working in assembly languages. So assembly languages still is more demanding than Java, MATLAB, LabVIEW or JavaScript. Okay, because it can interfere, it can interact more easily with the hardware. Okay, compared to all other languages, because these are high level languages. So that's why we are going to focus on embedded C in this course. Okay, and we discussed this part in the last lecture, and here this is important. 32-bit processors are now becoming more and more trendy in 2020. Okay, so preferably you should work with 32-bit processors, and that's why if you check the board which I have suggested, okay, Tiva C Launchpad, it is a 32-bit system. Okay, so in my opinion we are going to work in the latest trend. Okay, you are going to study the things which are actually hot even in 2020. So C along with 32-bit processor, a controller. Okay, when we use sensors, of course whenever you are using sensors or actuators, you will use signal conditioners. So these two will come together. Have you heard of closed loop control systems? How many of you have gone through that subject, control systems? Almost everyone, right? So what are the things that you have to keep in mind when you are designing any system using control system? Any essence from that subject, control system subject? What is the essence of that subject? Anyone? What was the final essence of that subject, control system? उस सब्जेक्ट को पढ़ने से क्या बेनिफिट मिला आपको, या किसी को भी पढ़ने से क्या सीखना चाहिए उस सब्जेक्ट को? एनीवन? If suppose someone asks you summarize the subject control system or summarize the importance of the subject control system in one line, what will be your answer?
How can we control the output
Anyone
as
else?
per our needs?
Okay, anyone else?
सिस्टम स्टेबिलिटी के बारे में.
Yeah, so system stability, yeah. So that means indirectly you can say by knowing the subject like control system, you can know whether the system will remain stable or not. Stable or not. That means control system provides you, or the subject provides you the knowledge about the stability of any system. And it is very important. Stable means the system will keep on working for a very long time period, or you can say for an infinite time period almost. It will it will be stable, it will be working normally for a very, 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 very long time period. For even when there are so many variables changing around it, like temperature, the humidity, the pressure, so many things, or electrical voltage, current, amplifications, all these things, when they are changing, even when they are changing, the system will remain stable or not. Okay, so by knowing that subject, you can know whether the system will remain stable or it will become unstable. Unstable means you cannot predict how the system is going to behave. It may oscillate, it may burn out, it may even stop, it may generate damping and so on. So for that, control actually is generated by using closed loop controls, like closed loop negative feedback or positive feedback stuffs. So this is required. So any embedded system engineer should be good to understand this kind of systems like closed loop control. That means you should not make the system unstable. Okay, measure important system variables. Every embedded system designer should be able to measure important system variables. When we are saying system variables, it is not only voltage, current, temperature also. There may be so many other parameters also which an engineer should be able to measure properly. Measurement is not that simple. You should know how to handle CRO, power supplies, and so on. Okay, he should be measurement may need to used by the brain, leave it. Okay, now conditioning. When we are saying signal conditioning, then conditioning of the signal may be scaling. Scaling means amplification, de-amplification, so on. Offsetting means adding some DC voltage, subtracting some DC voltage, or so on. Filtering will be, when we say filtering in electronics, it is more related to frequencies, allowing some frequencies to go or work, or banning some frequencies to enter into the system. So when we say scaling, we are saying amplification. Okay, offsetting means plus or minus some DC voltages. Filtering means allowing some frequency or blocking some frequencies extra. So these kind of features or techniques should be should be very handy with the engineers who are actually entering into the embedded system. So whatever you have studied till date was related to either amplification. If you focus in the back, in the past, if you see what kind of subjects were taught to you, why those subjects were taught to you, you will come to a conclusion that actually this is going to help you when you are going to design a system like amplification, offsetting, frequency filtering, control systems, and all those. So this subject is going to include all those technologies or techniques and it will help to design your perfect systems. Okay. Now, other than that, a good engineer should be, or embedded system designer should be knowing all kind of different shields or sensors which are available in the market. So he always should go and keep on updating his vocabulary especially in the terms of the devices or sensors which he can use, like shields, like GPS, VGA, camera. How many types of cameras are there? When I am saying VGA, what other cameras are there? Anyone?
Infrared.
Infrared cameras are there, or other than VGA, other than VGA. I would recommend you to do one thing. Remember these things. Go and briefly study at least 1 or 2 pages related to these things. What are the important parameters related to these technologies or these shields? Important parameters. Okay, of these particular things. Like when we say Wi-Fi, you might be knowing Wi-Fi. I am going to use Wi-Fi module with my embedded system or with my microcontroller board. But do you know what is the frequency band? Do you know what is the data rate which is allowed in this spectrum? What is the bandwidth of Wi-Fi? What is the power generated? What is the power allowed in Wi-Fi? These kind of stuffs you don't know. You just know the word Wi-Fi. There are so many parameters like I said, frequency band, okay, central frequency, FC you can call central frequency, the allotted power which can be radiated by the Wi-Fi, okay. Then of course the data rate it can support, maximum data rate can support, and Wi-Fi the range it can support. Then of course how much power it requires, or how much DC power supplies are, what kind of DC power supplies are required to design these things. These kind of stuff you should know before going to select any particular solution. It is not that always go and you choose Wi-Fi. There are so many wireless modules or shields available. Okay, so do go study those things, understand at least few of these parameters, and then move into the domain. Otherwise, you cannot design a good system until unless you know the parameters, their limitations, important parameters and limitations. So keep a notebook with all these things and take their important parameters and limitations. For that, you can choose any data sheet and note those things, okay. And then of course we can discuss it when we are going to design your final project. Okay, now there are so many other alternatives to microcontrollers. I am just going to end the lecture here. It is not that you should always go and stick with the microcontrollers. There are so many other ICs with other different technologies are available, which actually are giving head-to-head competency to this microcontroller. They are competing with these microcontrollers, and of course, most of them are actually doing much better than the microcontrollers. So it is not that you always should go and use microcontrollers. Other than that, there are ASIC, CPLD, DSP chips, FPGA ICs, PLCs, along with the microcontroller. So these are all the market driving forces which are used to generate intelligent systems. I would recommend you to just briefly go and check what these things are. In the next class, we will be discussing more about it. And then after this, we'll be entering like this. You will be discussing this part. And then and then this is the last slide. After that, we will be, I believe next class we will be entering into the mathematics of embedded systems and then programming C. Okay. So I will recommend you just note down these technologies and study at least when to use these things, when not to use these things. Understood? Just at least you should know when an engineer should use ASIC, CPLD, DSP, FPGA, PLC, or microcontrollers or microprocessors, or when he should not use ASIC, CPLD, DSP chips, FPGA, PLC, or microprocessors. At least you should know these things, and then you should use those technologies, because when you are going to say I am an embedded system designer, the company or the interviewer will be always looking into what other things that you know other than the microcontrollers, because many companies are not using microcontrollers only, they are using these technologies also. Just go and understand when you need it and when you don't need it. Okay, and with that I am going to end the lecture. If you have any doubts, you can drop it in the classroom and we can discuss it in the next lecture. Okay, thank you.